Hi there, Mr. Sutton with the AB Calculus 612 Extra Practice Number 1 Solutions on area between curves. On this no calculator problem, we need to find the area enclosed by y equals x squared plus 1 and y equals 5. So we're going to start by seeing where these things equal each other. So x squared plus 1 equals 5. We want to find the intersection points because that'll give us our limits of integration. So subtracting 5 from both sides, I've got x squared minus 4 equals 0. And let's see, if I add 4 to both sides and square root, I've got x equals plus or minus 2. Now you might be wondering why I did it this way instead of subtracting 1 over here and then square rooting. There's a method to my madness. I'm going to need this expression here where I've subtracted one function from the other a little bit later on in the problem. Not too far ahead, actually. Because now that I've got my limits of integration from negative 2 to 2, I need to take the integral. And I'm going to use absolute value, by the way, because I'm not sure which of these functions is higher up. It's probably the y equals 5, because this is a parabola opening up. But let's just use absolute value to be sure. And now I'm going to have one function minus the other inside to give me those distances that I'm adding together to get the total area. So we need, I'm going to just do this one minus this one, which happens to be x squared minus 4 dx, close my absolute value. And now let me take my antiderivative from left to right. So this is going to be 1/3 x cubed minus 4x evaluated from negative 2 to 2. Still have my absolute value here. So that's all this stuff with 2 plugged in minus all this stuff with negative 2 plugged in. And since this is not free response, I can't unfortunately just leave it like this. I've got to evaluate it all the way down to one of these answers here. So let's do it box by box. In this first one, this is going to be, let's see, 8/3 minus 8. Well, that's really 8/3 minus 24/3, which is negative 16/3. And then for this next one, something pretty similar. I've got, this is now going to be negative 8/3 plus 8. So that's going to be a positive 16/3. But I'm subtracting it because of this minus out here. So minus 16/3 again. So this ends up being negative 32 over 3, which the absolute value turns into a positive 32 over 3. So that'll give us choice D. For this problem, we have a shaded region in the graph, and we want to figure out which of these represents its area. So we're using integrals for this. That means our general format, since we're expressing these as functions of x, we're going to go left to right. So I'm going to have the integral from the leftmost x value to the rightmost x value of the region here. And then we're going to have top minus bottom function as my kind of integrand, my inner thing going on here. So in terms of this problem, left and right, well, the leftmost x value is a according to the graph. The rightmost x value where these things cross is c. So I have an integral from a to c. And now top minus bottom, the top function is this f function right here. The bottom function is g. I want to subtract top minus bottom, so I'm always getting positive area. So that's going to be f of x minus g of x dx. Do I have an answer choice that looks like that? Looks like choice D. Careful. C and D are pretty similar, but C, they were subtracting the wrong way. This would have given you negative area. Only D gives you positive area between those two. For this problem, I want the area enclosed by this rational function and this polynomial. To make my life a little bit easier in terms of writing things, I'm going to rename this first one to be f of x, and this other one, this polynomial, I'll call g of x. Now, to figure this problem out, I need to graph these, and I need to know where f and g intersect. So I'm going to set these equal to each other and actually solve for that intersection place on the graph. So here we are. I've got both of these things entered in my y equals. No idea where I should be looking in terms of a window. So let me do zoom 6 and see what these things look like. All right, so there's the first one. Here's the other one. I'm going to zoom in a little bit. Let me do a zoom, I don't know, zoom 4. That takes me a little further in. And now I have a slightly clearer picture. This is the area that we want, this region in here where they bound things. So I need to find these two intersection places. So for this one on the left, let me do second trace and then intersect. Move my spider this way. Press enter 3 times. And I get some number, negative 0.9319. I'm immediately going to quit out of here, and I'm going to store that as some letter. I'm going to call this one P. I could have chosen any of the letters, though, but I like P and Q for these graphs. Next, let me go back to my graph, and there it is again. Let me do second trace intersect and find my other intersection place over here. Enter 1, 2, 3 times, and I get pretty much the symmetrical point on the other side. Let me quit out and store that as alpha Q. So now I have these two values ready to go when I need them. So there was my graph, and I'm going to say that these intersect at x equals P equals, here's the one on the left, x equals Q equals this other one on the right, and now I can just use those without having to rewrite the whole number. Okay, so what do I actually do with all this? Well, I'm going to need an integral from the left to the right, so from P to Q, and inside I'm going to do top minus bottom. So that's going to be, let's see, this parabola is the bottom one, so the other one's the top one. So I'm going to do f of x minus g of x to get top minus bottom to get positive area. And now let me do all this on my calculator. So I've got math 9 integral from alpha p to alpha q, and then inside, if I'm doing f minus g, that's going to be y1 minus y2 based on where I put things in my calculator. So we've got alpha trace to get y1, alpha trace again to pull up y2, and dx, this thing, x, I don't need that weird menu. All right, press enter, and that's 1.582. So that's going to give me choice C. On this problem, we have a shaded region bounded by this weird square root cosine graph. That's this stuff in here, and also the lines x equals -7, x equals 7, and y equals 2. We want to find the area of that shaded region. So to do this, my overall strategy, I want to take the area of this rectangle that the shaded region includes, and I want to subtract this white area here, represented as the area under this square root cosine curve. So to do that, I need to find an integral to represent this cosine stuff, and then I can subtract it from my rectangle area. All right, so to find the integral, I need limits of integration. I need to know where this thing begins and ends on the x-axis. So I'm going to go ahead and set this stuff equal to 0. And I could try doing this on a calculator, and I can get a pretty good sense of it, but you're not going to be able to find the exact intersection. It's just weird the way this kind of semicircle ovalish thing works out on your calculator. But we can very quickly solve it algebraically. So square both sides, and now I'm going to do inverse cosine. So where does cosine of something equal 0? Well, cosine, the x values, that's going to be 0 on the unit circle at pi over 2 and 3 pi over 2. Although this case we have negative numbers, so I'm going to say negative pi over 2 and pi over 2. And now to actually get x, I have to get rid of this pi over 10 business. So I'm going to start by dividing everything by pi. That just gives me -1/2, +1/2. And then I'll multiply everything by 10. So that's going to be a -5 and a +5. So then the stuff inside here, this is going to be the integral from -5 to +5 of this function here. All right, putting it all together for my overall area, I've got the area of my rectangle, which is just going to be, let's see here, we have a base of 14 from -7 to 7. We have a height of 2, so 14 times 2, minus the integral from -5 to 5 of this weird square root function, and at this point, it's up to the calculator. To make my life just a little bit easier, I'm going to enter this function as y1. I mean, it's pay me now or pay me later. You've got to do it at some point. But if I keep it as y1, then I don't have to worry about parentheses or any other weirdness involving that. So now I had, let's see here, 14 times 2 minus math 9 integral from, we said, -5 to 5 of this function, which I now have stored as y1, so I don't have to mess with it again, and then dx, all that coming out to how much? How much is that integral in the window? All right, this one's taken a while to think about. Oh, we got it, 20.372. So don't stop believing, right? The answer will come eventually. So that's choice C. On this problem, we're told that there's a region bounded by y equals 1 over x, the x-axis, the line x equals m, and the line x equals 2m with m values greater than 0. We want the area. So let me set up a general kind of area integral for this. So what are we going from? We're going from the x value m to the x value 2m, which is obviously more than m because the m values are positive. So an integral from m to 2m of, well, this function here, and I'm going to stick that initially in absolute value just to be on the safe side, but as it turns out, this function is going to be positive wherever the x values are positive, and we know all the x values are positive because m, which is what these x's here are based on, is also positive. So long story short, we don't need the absolute value outside, and when I take the antiderivative and get ln of absolute value of x, I actually don't need that absolute value with the ln either, because I'm not going to be plugging in 0 or negative x values. All right, so let me just evaluate this. We've got ln of 2m minus ln of m. That's nothing that's going to help us with the answer choices, so let's simplify this a little bit. Since I'm subtracting logs, I can divide the things inside. This is actually ln of 2m over m, which is just ln of 2. Okay, so we're told that the area is ln of 2. So what does that mean in terms of all of this stuff? Well, the area, it doesn't really matter what m is. This is always going to be the case. So the area appears to just be independent of m. Since the area is a constant, we don't care what m is. That would be choice A. For this problem, they're told that the average value of a function over the interval 2 to 4 is 3. F is greater than or equal to 0 for all x in 2 to 4, and we want the area enclosed by the graph y equals f of x, the lines x equals 2, and x equals 4, and the x-axis. So this is actually looks like a lot to think about, but it turns out not to be as nasty as it looks at first glance. We're going to dig in with this average value part. So let's set up an integral involving the average value, because they told us what the average value is. So we might be able to use that to figure out the actual area under the graph of f. So we're going to start with 1 over the interval length. That's going to be 1 over 4 minus 2 times the integral of 2 to 4, from 2 to 4, of, and they said the average value of the function f. They didn't tell us what f was. We're just going to put f of x dx in here. They did tell us that this average value takes on a value of 3. Great. So we wanted to figure out the area of the region enclosed by f of x. Well, that area that you're looking for between 2 and 4 is this integral right here, without all this stuff out in front. So we're actually just going to multiply both sides by, let's see, this is 1 over 2, so multiply both sides by 2 to get 6 over there. And now this says pretty much exactly the area under my curve from 2 to 4 has a value of 6. So that would be choice B. For this problem, they want to know the area of the region in the first quadrant enclosed by cosine of x, and the y-axis. So I'm going to start by just renaming these. I'm going to call cosine of x f of x, and y equals x, I'll call that g of x, just so it's easier to keep them separated. And I need to figure out where these two things intersect. That'll give me my limits of integration for this region that I'm trying to find the area of. So I'm going to set f of x equal to g of x, and I'm going to solve that on my grapher. So here I am in y equals, putting those things in there, and I'm not really sure what window to graph these on, so let me just do zoom 6. That'll give me a nice window, 10 in every direction. There's my cosine curve. There's y equals x, and we see that there's a few places in here that could be the region we're looking for. So I'm going to do zoom 4. That just gets me a little bit closer. And now I should have a pretty good picture of the area I'm looking for. So it's going to be this area right here that's between the y-axis and our two curves. So in order to find that, let me get my limits of integration. Let me get my intersection between these two functions. So that's going to be second trace and then option 5 for intersect. Let me move my spider a little bit closer to the intersection. Press enter 1, 2, 3 times. And that gives me this x value, 0.7391 if we round it off. I'm going to immediately quit out of the graphing screen, and I'm going to store that value that I just got as some variable. I'm going to call it a p. It's actually a constant. So alpha p You could use any letter you want. I just like P for these problems. And I'm also going to write that on my paper here. So my intersection is going to be x equals P, which is approximately 0.7391. And now to actually find the area in this little region here, I need to do the integral from 0 to P. And now for my integrand, I need to do top minus bottom. The top function in this case is cosine. Bottom function is y equals x. So I'm going to do basically f of x minus g of x dx in there. And let me actually plug this in my calculator. So I've got math 9 from 0 to, we said P, so alpha P, that's where I stored this number here. And in here I've just essentially got y1 minus y2. So let me pull those up with alpha trace. There we go. y2. And then we have dx. All of that's coming out to about 0.400 if we take it out 3 decimals. And that's choice C.